Everyone remembers the small block Chevy. It's the engine that powered a generation, the motor that built hot rods, the legend that never dies. But what if I told you that the real secret to General Motors' enduring dominance wasn't the small block at all? What if the answer was bigger, more power, far more important than anyone gives it credit for? The truth is, GM's big block V8 didn't just compete with the small block. In many ways, it defined what American power really means. While enthusiasts debate compression ratios and camshaft profiles, the big block quietly won races, pulled loads, and powered dreams across 5 decades of American life. It survived oil crises, emissions laws, and corporate reshuffling that killed nearly every other engine of its era. And here's the kicker, it's still winning today, in applications the original engineers never imagined. This isn't just a story about cubic inches and horsepower. It's about why some machines transcend their time, why certain designs become immortal, and why the biggest engine General Motors ever built turned out to be the most important one they never stopped needing. The story begins in Tonawanda, New York, in the winter of 1964. General Motors had a problem. Their small block V8 had been a runaway success since 1955, powering everything from Corvettes to station wagons with reliable, affordable performance. But as the 1960s roared forward, power was becoming the only currency that mattered in America. Ford had their big block FE series, Chrysler had unleashed the Hemi, and suddenly 327 cubic inches didn't feel like enough anymore. GM needed something bigger, something that could compete in NASCAR, something that could haul trailers and pull boats while also humiliating Fords at the drag strip on Saturday night. But they didn't just need more power, they needed an engine that could be everything to everyone. An engine that could work as hard on Monday morning as it played on Sunday afternoon. So they assembled a team at the Tonawanda engine plant, the same facility that had been building power plants since the 1930s, and gave them a mandate that was simple and impossible at the same time. Build the greatest American V8 ever conceived. Build something that would last forever. The team was led by engineers who understood that displacement was only part of the equation. They knew that an engine's real strength came from its architecture, from the fundamental decisions about bore spacing, deck height, and block rigidity that determined whether a motor would survive or disintegrate under stress. They studied that of failures from other manufacturers. They analyzed what made engines fail at Daytona and Le Mans, and they designed something that prioritized durability over everything else. This wasn't going to be a race engine that happened to work on the street. It was going to be a street engine that could win races without modification. That philosophy, that core belief in over-engineering everything, would define the big block for its entire existence. The first version arrived in 1965 as the Mark IV Big Block, displacing 396 cubic inches in its initial form. But that number was deceiving because the engine's real innovation was invisible to anyone who didn't tear it down to the bare block. GM's engineers had created an architecture with massive potential for growth. The cylinder bore spacing was wider than the small block, which meant pistons could grow larger without running into each other. The deck height was taller, which allowed for longer strokes and more displacement without compromising rod angles or piston speeds. And most importantly, the block itself was a fortress. It featured 4-bolt main bearing caps instead of the typical 2-bolt design, which meant the crankshaft was held in place with twice the security. That might sound like a minor detail, but it was the difference between an engine that could survive sustained high RPM operation and one that would grenade itself after a few hard passes down the drag strip. The main bearing journals were massive, spreading the load across more surface area and reducing the stress on any single point. And the block casting itself was substantially thicker than competitors. Additional ribbing and reinforcement in areas that typically cracked or failed under load. This wasn't an engine designed to meet a specification. It was an engine designed to exceed any specification anyone could imagine. The original 396 cubic inch version made 325 horsepower in its mildest form, which was respectable, but not earth-shattering. What mattered was the potential. Within a year, GM had stretched the bore and stroke to create the 427 cubic inch version, which could be ordered with up to 130 horsepower in factory trim, and that was just the beginning. The big block's architecture allowed for displacement increases that seemed almost effortless. Bore it out a bit, stroke it a bit more, and suddenly you had 454 cubic inches, 7.5 liters of American Fury that made 450 horsepower and 500 pound-feet of torque without breaking a sweat. But the real genius wasn't in the peak numbers. It was in how the engine made power. The long stroke meant torque arrived low in the rev range and stayed strong all the way through the power band. This was an engine that pulled like a diesel, but revved like a race motor. It could lug a heavy load from idle without complaining, but it could also spin to 5,000 revolutions per minute with confidence. That versatility made it perfect for everything from luxury cars to pickup trucks to sports cars to racing applications. The golden era of the big block began in 1966 and lasted through the early 1970s. This was the period when cubic inches equaled power, when gasoline was cheap, and when Americans measured their self-worth by the size of the engine under the hood. GM put the big block into everything. The Chevelle SS got it, the Corvette got it, the Camaro Z28 got it, El Caminos, Impalas, and even full-size pickup trucks got it. Each application revealed another dimension of the engine's versatility. In the Corvette, it made the car a legitimate supercar competitor, capable of embarrassing Ferraris and Porsches at a fraction of the cost. In the Chevelle, it created one of the most iconic muscle cars ever built, a mid-size sedan with enough power to terrify anyone who underestimated it. And in trucks, it proved that an engine designed for performance could also work for a living, hauling loads and towing trailers with the same effortless authority it brought to the racetrack. The 454 version became legendary almost immediately. It was rated at 450 horsepower, but everyone knew that number was conservative. Real-world dyno testing showed output closer to 500 horses, and the torque was even more understated. This was an engine that could light up the tires from a standstill and keep them spinning through multiple gears. The LS6 version, offered only in 1970, was the absolute peak, a factory race engine that somehow passed emissions and safety standards long enough to be sold to the public. It featured a high-lift camshaft, improved cylinder heads with better flow characteristics, and a high-performance intake manifold that fed air and fuel with minimal restriction. The result was an engine that could propel a 3,500-pound car through the quarter mile in the high 13s and hit 60 miles per hour in under 6 seconds. Those numbers would still be impressive today. In 1970, they were supernatural, but the big block's dominance wasn't just about straight-line speed, it was about respect. When you opened the hood of a car with a big block, people knew you were serious. The engine filled the entire engine bay, a massive block of cast iron and aluminum that looked like it had been carved from a single piece of American granite. The sound was unmistakable, a deep, rumbling idle that you felt in your chest, an exhaust note that announced your presence 3 blocks away. And the acceleration was intoxicating. Modern cars are faster in every measurable way, but they lack the drama, the violence, the sheer mechanical fury of a big block at full throttle. When you planted your foot in a big block car, the front end would lift, the rear would squat, and the tires would break loose in a cloud of smoke that could be seen from space. This wasn't transportation, it was theater. It was emotion made mechanical. The racing success of the big block cemented its legendary status in ways that street performance alone never could. At drag strips across America, big block Chevelles and Camaros dominated their classes, running times that seemed impossible for street-legal cars. Professional drag racers quickly discovered that the big block's bulletproof bottom end could handle nitrous oxide injection, supercharging, and turbocharging with minimal internal modifications. The same 4-bolt mains and massive crankshaft journals that made the engine reliable on the street made it capable of surviving power levels that would destroy lesser engines. By the early 1970s, modified big blocks were making over 1,000 horsepower in competition trim, and they were doing it reliably enough to run multiple passes without requiring teardowns between rounds. That kind of durability gave racers confidence, and confidence translated into aggressive tuning and even more wins. On the oval tracks, the big block proved equally dominant. NASCAR teams found that the engine's torque curve was perfect for maintaining speed through corners and accelerating hard down the straights. The architecture's ability to accept larger displacement made it competitive even when rules limited certain modifications. And the aftermarket quickly developed specialized components, lighter connecting rods, forged aluminum pistons, and racing camshafts that transformed the street engine into a purpose-built competition power plant without requiring a complete redesign. Even in road racing, where the big block's weight was a disadvantage, teams found success by exploiting the engine's massive power advantage to overcome the handling deficit. The Corvette's dominance in SCCA racing During the late 1960s and early 1970s owed as much to big block torque as it did to the chassis engineers who made the car handle. Drivers learned to use power to rotate the car through corners, exploiting the rear weight bias that the heavy engine created. What looked like crude brute force was actually a sophisticated racing technique that played to the big block's strengths. But nothing in Detroit lasts forever. By the early 1970s, the world was changing in ways that nobody in Tonawanda could have predicted. The oil crisis hit in 1973, and suddenly fuel economy mattered more than horsepower. Insurance companies had been waging war on performance cars since the late 60s, and by the early 70s, they'd won. Premiums for big block cars were so high that young buyers simply couldn't afford them. And then came emissions regulation. The Clean Air Act demanded catalytic converters, unleaded fuel, and dramatic reductions in hydrocarbon and nitrogen oxide emissions. The easiest way to meet those standards was to strangle the engines with restrictive intake and exhaust systems, retard the timing, and lower the compression ratios until the engines barely ran. By 1975, the once mighty big block had been neutered. The 454 was down to 215 horsepower in some applications, less than half its peak output just 5 years earlier. The LS6 was gone, the high-performance versions were discontinued, and the entire muscle car era seemed to be dying a slow, painful death. GM considered killing the big block entirely. After all, the small block could be emissions-tuned more easily, it was lighter and more fuel-efficient, and it could make adequate power for most applications. But here's where the big block's real genius revealed itself. While the performance versions were dying, the truck versions were thriving. Pickup trucks didn't need to meet the same strict emission standards as passenger cars, which meant the big block could continue to make real power in commercial applications. Construction companies needed trucks that could pull heavy trailers. Farmers needed engines that could run all day under load without overheating or failing. And recreational users needed power to tow boats and RVs to lakes and campsites across America. The big block did all of that without complaint. So while the muscle car versions faded into memory, the truck versions soldiered on through the 1980s and into the 1990s. GM kept refining the design, adding fuel injection to improve efficiency and drivability, strengthening components to handle even more stress, and adapting it to new applications as they emerged. The architecture that had been designed for maximum durability in 1964 turned out to be perfect for the demands of heavy-duty truck work 30 years later. The transition to fuel injection in the 1990s represented the big block's most significant evolution since its original introduction. General Motors understood that carburetors were fundamentally limited in their ability to precisely control fuel delivery across varying conditions. A carburetor works through mechanical principles, vacuum, float levels, and jets, that can be tuned for specific conditions but struggle to adapt to changing variables like altitude, temperature, and load. Fuel injection, by contrast, uses sensors and computers to measure exactly what the engine needs at any given moment and delivers precisely that amount of fuel. The result is better power, better fuel economy, better emissions, and better drivability in every condition. But adapting fuel injection to the big block wasn't as simple as bolting on some injectors and calling it done. The engineers had to completely redesign the intake manifold to accommodate individual fuel injectors for each cylinder. They developed new cylinder heads with improved port designs that maximized airflow while maintaining good low-end torque. They created new engine management computers that could handle the big block's unique characteristics: the long stroke, the heavy rotating assembly, the massive displacement. And they did all of this while maintaining compatibility with the basic architecture that had been in production for 3 decades. The brilliance was in the execution. When the Vortec 8000 series debuted, it didn't feel like a compromised old design limping into the modern era. It felt like a thoroughly modern engine that happened to share its basic dimensions with a classic. The power was there, over 300 horsepower in stock form, with torque numbers that exceeded 400 pound-feet. But now that power came with smooth, idle quality, instant cold starts, and emissions levels that met increasingly strict federal standards. The fuel injection system eliminated the tuning headaches that plagued carbureted big blocks, especially in high-altitude locations where thin air wreaked havoc on jetting and mixture ratios. By the early 1990s, General Motors made a decision that shocked the industry. They announced the next generation of their big block truck engine, the Vortec 8000 series. This wasn't a warmed-over version of the old design. It was a complete reimagining that kept the core architecture while modernizing everything else. The new engine featured electronic fuel injection with individual injectors for each cylinder, computer-controlled ignition timing that optimized performance across the entire operating range, and vastly improved cylinder head designs that flowed more air with less restriction. The displacement options range from 454 to 502 cubic inches, and the power output was stunning. Even in emissions-compliant form, the new big block made over 300 horsepower and more than 400 pound-feet of torque. That was more power than the original 1965 version, in an engine that met 1990s emission standards and got better fuel economy. The secret was efficiency. Modern engine management systems meant the computer could adjust fuel delivery and ignition timing thousands of times per second, optimizing combustion in ways that mechanical systems could never match. The result was an engine that made more power with less fuel and fewer emissions than should have been possible from an architecture that was nearly 30 years old. But the real surprise came in how the aftermarket responded. Hot rodders and racers had never stopped loving the big block, but the old carbureted versions were difficult to tune and impossible to pass emissions testing in many states. The new fuel-injected versions solved both problems. Suddenly, you could build a big block that made serious power, idled smoothly, started instantly in any weather, and passed emissions testing without any tricks or modifications. The aftermarket exploded with performance parts designed for the new platform. Companies developed upgraded camshafts, better flowing cylinder heads, stronger rotating assemblies, and forced induction systems that could make the big block produce power numbers that would have seemed impossible just a decade earlier. 1,000 horsepower streetcars became almost common. 2,000 horsepower race cars became achievable. And the big block's reputation for bulletproof durability meant those power levels didn't result in immediate catastrophic failure. The engine could take the abuse and keep running. The marine industry became an unexpected but crucial market for the big block's continued success. Boat builders needed engines that could deliver sustained high-power output in the harshest possible environment. Saltwater corrosion, constant vibration, and operation at or near maximum output for extended periods created demands that few automotive engines could meet. But the big block's overbuilt architecture made it ideal for marine applications. The thick block castings resisted corrosion better than lighter designs. The heavy crankshaft and strong bottom end could handle sustained high RPM operation without the bearing failures that plagued lesser engines. And the torque curve was perfect for pushing heavy boats onto plane and maintaining speed against wind and current. Marine versions of the big block were developed with specialized components, closed cooling systems that used heat exchangers instead of exposing the engine internals to corrosive salt water, special corrosion-resistant coatings on external components, and heavy-duty electrical systems that could survive the humid marine environment. These engines powered everything from fishing boats to luxury cruisers to offshore racing boats that competed for speed records and championship titles. The offshore racing community, in particular, embraced the big block with enthusiasm that bordered on obsession. These boats needed engines that could make over 1,000 horsepower reliably, because races were won or lost based on sustained speed over rough water. Engine failures meant retirements, and retirements meant losses. The big block's durability made it the engine of choice, and specialized marine engine builders developed big block combinations that made astonishing power while remaining reliable enough to finish races. Twin big block installations became common in larger offshore boats, with each engine making between 800 and 1,200 horsepower. These boats could exceed speeds of 100 miles per hour on open water, which required engines that could sustain maximum output for extended periods without overheating or failing. The big block delivered race after race, season after season. The industrial and agricultural sectors discovered their own uses for the big block's unique combination of power and durability. Farmers found that big block-powered equipment could handle the sustained heavy loads of plowing, harvesting, and hauling that destroyed lighter engines. The engine's massive low-end torque meant tractors and combines could pull through heavy soil or thick crops without lugging down or stalling. Construction equipment manufacturers installed big blocks in everything from concrete mixers to compressors to generators, discovering that the engine's ability to run at constant high output for hours or days at a time made it ideal for stationary power applications. Water pump stations in agricultural regions used big block engines to move irrigation water, running continuously during growing seasons, with maintenance intervals measured in thousands of hours rather than hundreds. Oilfield equipment relied on big blocks to power drilling rigs and pumping equipment in remote locations where reliability was more important than fuel economy. These industrial applications rarely made headlines or appeared in enthusiast magazines, but they represented a massive market that kept the big block relevant and profitable long after the muscle car era ended. The engines built for these applications were detuned for longevity rather than peak power, but they shared the same fundamental architecture that made the performance versions legendary. A big block running a water pump in California's Central Valley had the same 4-bolt mains, the same oversized bearing journals, and the same bulletproof block casting as the LS6 that powered a 1970 Chevelle. That commonality meant parts were readily available, mechanics knew how to work on them, and owners could count on decades of reliable service. The industrial big blocks proved that the engine's design was so fundamentally sound that it could succeed in applications far removed from its original purpose. Today, decades after the first big block rolled off the assembly line in Tonawanda, the design is still winning, not in showrooms. GM officially discontinued the last passenger car big block in the early 2000s, but in the places that really matter to enthusiasts. Drag strips across America are dominated by big block-powered cars running in the 9s and 10s. Circle track racing still relies heavily on big block power for classes where cubic inch limits allow it. Marine applications use big block-based engines to power everything from ski boats to offshore racing boats. And the custom and hot rod world has never stopped building cars around the big block architecture. Why? Because the fundamental engineering decisions made in 1964 are still valid today. The wide bore spacing still allows for massive displacement increases. The tall deck height still accommodates long strokes for torque production. The 4-bolt mains and thick block castings still provide the durability needed for high-power application. And the aftermarket support means you can build virtually any combination you can imagine, from mild street cruisers to all-out race engines that make over 3,000 horsepower. Modern technology has only enhanced the design. Computer-aided design allows for optimization that wasn't possible in the 60s. CNC machining creates tolerances that hand-fitting couldn't match. And materials science has produced aluminum blocks that are lighter than the original iron castings but just as strong. Companies like Dart, World Products, and GM Performance Parts sell big block components that are better in every measurable way than the original factory parts. Yet they all bolt together because the fundamental architecture hasn't changed. That interchangeability across 6 decades of production is almost unheard of in the automotive world. You can take a cylinder head designed in 2020 and bolt it onto a block cast in 1968, and it will work perfectly. That kind of longevity comes from getting the fundamentals right the first time and refusing to compromise on quality or durability. The engineers at Tonawanda didn't just design an engine for their era. They designed an engine for all eras. The aftermarket's continued investment in big block technology reveals just how healthy the ecosystem remains. Every year, new products are developed that push the envelope of what's possible with the basic architecture. Cylinder heads with CNC-ported runners that flow over 400 cubic feet per minute are now available off the shelf. Billet crankshafts, machined from solid steel forgings, can handle loads that would have destroyed the original cast iron cranks. Connecting rods made from aerospace-grade materials weigh less while providing greater strength. And engine management systems developed specifically for big block applications allow tuners to extract every last horsepower while maintaining drivability and reliability. The availability of complete aftermarket blocks has been particularly significant for the big block's continued relevance. Companies like Dart manufacture aluminum and iron blocks that improve on the original design in every measurable way. These blocks feature thicker deck surfaces to prevent head gasket failure, priority main oiling systems that ensure the crankshaft bearings get oil before anything else, and increased coolant capacity to improve thermal management. They're available in various deck heights and bore spacings, which allows builders to create custom displacement combinations that weren't possible with factory blocks. A builder can start with a Dart block, add a stroker crankshaft for increased displacement, install modern cylinder heads with excellent flow characteristics, and create an engine that makes 700 horsepower naturally aspirated. Without nitrous, without forced induction, just good old-fashioned cubic inches and airflow. Add a supercharger or turbocharger system, and that same combination can make 1,500 horsepower or more. The big block's architecture can handle it, which is why serious engine builders continue to choose it for applications where maximum power and reliability are both required. The educational value of the big block cannot be overstated for those learning the fundamentals of internal combustion engines. Because the design is relatively simple and extremely well documented, it serves as an ideal teaching platform for understanding how engines work. Vocational schools and community colleges often use big block engines in their automotive programs because students can disassemble them completely with basic hand tools, see exactly how each component functions, and understand the relationship between design choices and performance outcomes. The big block teaches that displacement matters, that rod ratios affect piston speeds and bearing loads, that camshaft timing determines power delivery, and that proper clearances and tolerances are essential for reliability. These lessons learned on a big block transfer directly to understanding modern engines, even though contemporary power plants use overhead cams, variable valve timing, and direct injection. The fundamentals remain the same. Air and fuel must be mixed, compressed, ignited, and expelled efficiently. The big block does all of that with components you can see, touch, and understand without a computer science degree. That accessibility has created generations of self-taught engine builders who started by rebuilding a big block in their garage and went on to careers in automotive performance, racing, or engineering. The engine's forgiving nature also helps beginners learn from mistakes without catastrophic consequences. Mess up the valve lash adjustment on a big block, and it'll run rough, but probably won't destroy itself. Make the same mistake on a modern interference engine with overhead cams, and you might bend every valve in the motor. That forgiveness encourages experimentation and learning, which builds the kind of deep mechanical understanding that can't be taught from textbooks alone. The legacy of the big block extends far beyond the engine itself. It taught American engineers that overbuilding wasn't wasteful. It was essential for creating products that lasted. It proved that versatility was more valuable than specialization. An engine that could work in a sports car, a muscle car, a pickup truck, and a race car was more useful than one optimized for a single application. And it demonstrated that sometimes the best solution to new problems is refining old ideas rather than starting from scratch. That philosophy influenced everything GM built afterward. The LS series small block that replaced the big block in performance applications borrowed heavily from the big block's playbook. Wide bore spacing for future growth, priority on durability over minimum weight, and architecture designed for easy modification. Even today's modern engines from GM show the influence of the big block's design philosophy. The big block also created a culture. Entire generations of American gearheads learned to wrench on these engines. They learned that with basic hand tools and a factory service manual, you could disassemble, rebuild, and improve an engine in your garage. That accessibility created a relationship between owner and machine that's increasingly rare in the modern world of sealed assemblies and proprietary diagnostic tools. The big block was something you could understand, something you could fix, something you could make your own. And that hands-on connection built loyalty that transcends brand preference or objective performance measurements. People don't just respect the big block, they love it. They name their cars after it. They spend years searching for the perfect example. They invest fortunes in restoration and modification because it represents something more than transportation. It represents a time when machines had personality, when power was visceral and mechanical, and when driving something fast required skill and courage rather than just stability control and launch control software. The secret reason GM's big block still dominates decades later isn't really a secret at all. It's visible in every dimension of the design. Every choice the engineers made, every application where the engine proved itself superior. The big block dominates because it was designed to dominate. Not through clever marketing or corporate manipulation, but through fundamental engineering excellence. It dominates because when other engines failed, the big block kept running. When other manufacturers moved on to newer designs, the big block proved that newer wasn't always better. And when the world changed in ways nobody predicted, the big block adapted without losing its essential character. It's still the engine of choice for anyone who needs reliable power in amounts that smaller engines can't match. It's still the foundation for record-setting race cars. It's still the heart of dream builds and restoration projects. It's still teaching new generations of enthusiasts what American engineering looks like when it's done right. The big block didn't just survive, it thrived. And it did so by being exactly what it was designed to, the greatest American V8 ever conceived. Have you ever built a big block? Do you remember the first time you felt one at full throttle? The way it pinned you to the seat and made the world blur past the windows. Maybe you've got one sitting in your garage right now, waiting for the right project, the right car, the right moment to bring it back to life. The big block has that effect on people. It makes you want to create something, to build something, to be part of a tradition that stretches back 6 decades and forward into a future where internal combustion engines are increasingly rare and precious. If you've got a big block story, a race you won, a restoration you completed, a memory from the golden age of cubic inches, drop it in the comments below. And if you enjoyed this deep dive into why some engines become immortal, hit that subscribe button. For more stories about the machines, the engineers, and the moments that shaped American automotive history. Because these stories matter. They're part of who we are, part of what we built, and part of why we'll never stop loving the rumble of a big block at idle and the fury of one at full song.